So now we are going to do variational inference. So let's repeat what I told you last time. So the problem that we have, this is a kind of Bayesian representation of the problem. I have a prior latent distribution, PZ. I do know what is the conditional distribution of x given z. I do know these two guys. What I want to compute is what we call it evidence. What is evidence? Essentially, this is the marginal distribution of x. This is what we call it evidence in this framework, in the Bayesian framework. Okay? So you have z. This is your latent. It has passed through a stochastic process, which is described by this px given z. Now, for every sample of z, you can explain what is the distribution of x. Now you want to know what is the evidence of x, the particular value of x. One thing that you should keep in mind, x value is fixed here, right? X is one sample, one data sample, right? So you can think in our context, we are simply computing the likelihood using point x. That's it, right? So this is evidence. If you ask me, is evidence essentially likelihood? Well, practically yes, this is likelihood, right? But you do know that at the end of the day, we think of this P, the green P, to be one computational model. And then the blue P, the evidence, is going to be also a computational model. And when we compute this evidence, this is going to be the likelihood of the model, right? Likelihood is not the likelihood of the data, right? Likelihood of the model, right? So theoretically, evidence is the probability at the point, and likelihood is the function of the model, right? But at the end of the day, they are both the same thing in our particular application, okay? So simple, we have latent, we have the generator, we want to compute the likelihood, right? And want to find a way to do that, okay? Now, if you want to do it directly, so you told me this is very complex, you're right. Thinking of a Gaussian distribution and neural network. And you can say it in general, right? If even you think of this P distribution, P of x, the conditional distribution, and the prior distribution of the latent to be general distributions, this is always going to be the case, right? For instance, say I have my latent variable being discrete variable, right? So z is m-dimensional vector. Every single entry in this vector is one of the c possible values, right? If this is the case, when I want to compute the evidence, I mean, the integral is going to essentially be a summation, but I should compute this summation. How many cases do I need to consider to complete this summation, this marginalization? Z is m-dimensional. Every single entry of z has c different possibilities. C to power m, exactly. So you're going to have c to power m additions. So this means that computational evidence, if I want to do it directly, this is going to be exponentially complex in terms of the latent dimension, right? And given the practical cases we have, we're going to have a very big, I mean, it's true that this is much smaller than the data dimension, but it's still a very big dimension, right? The latent dimension. And this is very hard for us, right? So direct computation is impossible. And you can simply see that this is exponential. And then when you want to sample directly from a distribution, you deal with an exponentially hard problem. They are the same thing eventually, right? So at the end of the day, you're ending up with the same kind of complexity because they are naturally the same problems. Moral of the story, you cannot compute this evidence directly no matter what that distribution is. I mean, if it's as simple as Gaussian, you cannot do it. If it is a general distribution, forget about it, right? So that's the case. Now, when we cannot compute something directly, what do we do usually? We usually estimate it, right? We try to collect a bunch of samples, put them together, so that it's going to approximately give us the value that we want, right? So I can use the expression that I have for the evidence to simply come up with one simple estimation approach. So let's look at the evidence once again. So this is the expression for evidence, right? The evidence is this integral, right? Now, looking at this integral, forget about the guy which is in color blue, that conditional distribution. If you look at everything remained in green, what is that guy doing? If I integrate some function of x times distribution of x, what am I doing? Some function of z times distribution of z. If I do that, what am I doing? Expectation. You're computing expectation, right? So I can write down this integral in this form. Do you agree with me? So this is the expectation of the conditional distribution, right? Now, if I have something which is represented in form of an expectation, can I estimate it? Yes. I simply collect lots of samples, then I average on those samples, the same function. This is going to give me an estimate of what I want, right? So this is the Monte Carlo approach. We did it lots of times in this course, right? And I'm pretty sure you have done it in many other courses as well. So the key point here is that I can't estimate this guy because this is an expectation. I simply collect lots of samples with distribution pz, and then I put those samples inside this expression. I average it, right? At the particular point x, right? So this is quite easy to do. So I'm going to do the estimation, numerical estimation of that. This means that I'm going to collect lots of samples z, and I average them over the number of samples that I have, right? That is possible, right? And those samples of z that I'm generating, is it hard to generate them? No, because z is my latent. This is the distribution that I'm choosing. I can simply sample from it, right? ID Gaussian. So that is a kind of feasible way to do it. So this is tractable to sample from pz. This is tractable to compute p of x given z, because I have that distribution, so I can essentially compute this estimation. But if you compute this estimation, this is not going to be a very accurate estimation. So it's going to be a very high variance estimation. Can you guess why? And I don't expect that you see it immediately. But can you guess what could be the problem? I just want to bring the question in your mind. OK, so. Sorry? Kind of? Exactly. You need a lot of z. And if you just simply sample from the prior, a lot of it should be very, very large, right? So this is exactly the point, right? So the key point here is that if I go ahead and do this kind of estimation, the issue with this estimation is that, well, I'm going to get lots of z values, right? And at every single z value, I'm going to compute one essentially Gaussian distribution, right? That blue p is a Gaussian distribution, right? Now, the Gaussian distribution for me is something like this, right? Some distribution like this, right? And this is a distribution against x, right? Here is x. This is a distribution against x. Z value is going to specify this guy, right? Correct? But in my problem, x is fixed, right? Here is x. For example, x value is exactly this one. Right? Now, if I sample z, what is going to happen? The first sample is putting it here. The next sample maybe is something here, so it's going to take it here, right? Next sample is going to take it here, and so on, right? So my sample z1, for example, give me this guy. My sample z2 is somewhere here, so it's going to give me something like this. Next one, z3, is giving me something like this, and so on, right? Now, if I want to really have the value that I'm going to get, p of x given z, what is that value? Is the value at this point, right? And this value, most of the time, is something tiny, right? Because it's very hard that this z is going to exactly hit the point which is close to the x point, right? So most of the time it's going to happen around it. And there are a few times where I am within this vicinity, right? So this means that if I take samples, and samples from PZ, from the prior, and put it inside this expression, most of the time I end up with small samples, right? And then when I average all of them, I'm going to have a few non-small values and lots of small values, right? And this could be very high variance, right? Because essentially you do know that all of those small values are approximately 0, and they are useless samples, right? Everybody's clear what's happening here? So the challenge that is happening is that you're sampling from the prior of Z, and that prior could be, for instance, Gaussian, and Gaussian could happen anywhere, right? And most of the time, the value that you see is not really hitting the point that you want, right? So these samples of Z are not very good samples, put it that way, right? They are bad samples. And because of that, the estimation that you're going to get is going to be very high variance. So just a few of those samples are going to be useful. So they are going to give us some P of x given Z that are valuable, are useful, are having like non-zero values. And because of that, the estimation that we're going to have here, I mean, most of these samples are 0. So it's essentially like estimating with only a few samples, right? And estimating with only a few samples, this means that you're going to have a very high variance estimation. So Monte Carlo approach theoretically is working here. I mean, it's true, you can use Monte Carlo, but it's not going to give you a very good estimate. It's going to give you a very high variance estimate. And the main reason is that those samples Z that you get are not going to end you up with good samples of Px given Z, right? And you need those samples. You don't need really samples of Z directly, right? So this is the problem that we have here. If we really want to do this, we need huge data set. And it's not hard to see that being huge, it simply means that you need exponentially large number of samples. You need exactly as much as you needed for direct computation. So forget about it. That is not going to work at all. Everybody's clear? Questions? OK. So if that is clear, can you give me any solution for that? What can I do if I want to still use this Monte Carlo approach as we have here, but I don't have high variance? What is the key point that I need to modify to improve or reduce the variance? P of Z, you mean? You are somehow right. I need to have this P of Z somehow better, right? Or in other words, I need to sample from the right distribution, right? So the intuitive idea here is that if I could make a process, or if I could make some procedure, such that when I am sampling from Z, I am not going to just shoot everywhere. I am always shooting around X, right? Then I'm going to have lots of useful samples. Then with just a few samples, I'm going to get good estimate, right? This is the idea. So if I can, for instance, come up with one distribution Q of Z given X. And can you guess why I put given X here? Because I want that distribution to be for the particular X that I'm looking for, right? So I want to somehow hit everywhere around X. So if I can come up with one distribution Q Z given X, one distribution for Z, which depends on the particular X that I'm looking for, and this distribution has this property. Whatever Z I sample from it, it's going to hit around this X, right? If I can find such a distribution, then I'm going to use that distribution and sample from that distribution. Using that distribution, I am going to average my P of X given Z values, right? And it's going to give me a better estimate, lower variance. Did you get the idea? So simple moral of the story, you really don't want your Z to be just randomly shooting on the real axis, right? You want it to be somewhere around x, right? Now, one thing that you might ask me is that, so if I can sample from this distribution and use those samples, then that is going to give me a better estimate of the evidence. But one question that you might ask me here is that, well, you could write down that Monte Carlo expression because essentially we had that, marginalization, which we could write it down as a form of expectation on z, right? P of z, right? If you replace P of z with something else, then you are not taking expectation over P anymore. You're taking expectation over that distribution, right? Q, for instance. And this is not accurate anymore, right? But that is not hard to do, to modify. How can I do it? I want to somehow introduce that distribution Q, which I think is a very good distribution that I can sample with, but I don't know what that distribution is yet. Okay? So we're going to talk about it later. I want to introduce that Q into this equation some way, such that when I am writing down my estimator, it has Q inside it, right? How can I do it? This is the evidence expression that I want to compute, right? So I'm going to divide P by Q and multiply everything by Q. Is it fine? Does it change anything? No? Yes? It does not, right? If I just cancel out Q values, it's going to be the same thing, right? Now, looking on that expression, integral of something times Q, distribution on Z, dz. What is that guy? Expectation. Over which distribution? Q of Z given x, right? So I can say that this is expectation over Q of Z given x, right? And what should I write down here inside the expression, the expectation? P times P over Q, right? So anything left inside the integral is going to go inside the expectation, right? So now, looking at this guy, I am taking expectation over my good distribution of Z, right? This is the distribution which is going to give me good samples, right? And I have one expression here, which, again, I can compute using sampling, right? So if I just sample from this distribution Q and put those samples here, I can estimate this expression. But now I am using better samples because I claim that Q is the better distribution. Anybody knows what is this trick? What do we call it? This is what we call it importance sampling. So you know that there is a better distribution Q, which is going to give you more important samples. So instead of working with P, which is giving you bad samples, you just do this simple modification, and then you use samples from Q, right? So eventually you can estimate average with respect to one distribution using samples of another distribution. This is what we call it importance sampling. So everybody's clear what I'm doing here? So I can essentially write down my evidence as a new expectation, and that new expectation has this property that the samples given by the distribution of that expectation are better samples. So now I can simply use samples from Q to estimate evidence. This is what I wanted to do, so let me just write it down here. So if I want to do it by sampling, I am going to sample Q. So I'm going to take a bunch of samples Zi from Q. And then I take those samples and put it inside this expression. So Z is going to replace here everywhere. And then I'm going to average those samples, right? Everybody's clear? This is what we call it importance sampling. And the intuitive idea here is that samples coming from Q are more important. And because they are more important, I am going to, essentially, they are always going to be within vicinity where this p-value is quite large. And because of that, I can simply replace my expectation with this new form and then use those samples, right? There are more useful samples that are going to give me better estimator. Any question? No question? So you got the idea of importance sampling. So it's not really complicated mathematically, but intuitively it's sometimes counterintuitive. Like I'm using another distribution to average something on another distribution, but when it's giving you a better sample, it's a way to go, right? This is why importance sampling is something. Okay, cool. Now, if you use importance sampling, eventually the estimate that you're going to get for your evidence is going to be a less variance. So it's going to have less variance. And this is a good thing. Eventually, if you can come up with the right choice of Q, then you're going to have like a good estimator, and then instead of evidence, you can use that good estimator. Okay, one thing here, again, I want to emphasize is that this x value here is all the time fixed, right? So x is the point where we are computing the evidence, right? I am not changing x. I'm talking about one single data sample, right? The thing that I am sampling from is z, right? And that z I can simply sample because I have everything inside this expression, right? This p of x given z is the one given by the problem to us, right? I can put z inside this expression and compute it. Pz is my prior distribution. Again, I can compute it. This q, I told you that I know this q. I haven't yet found out a way to come up with a good choice of q, but I assume that I know q, right? If I know q, I can again compute its value at the particular point, right? Everybody's clear? So everything inside this expression I can compute, and nothing, x is not changing at all. The thing that is being sampled is z, actually, okay? So don't get confused. Cool. Great. So importance sampling tells us if you want to estimate evidence, go and find the right choice of Q, and then you use importance sampling to estimate it, right? And this is going to be a good estimate. But then you might ask me, okay, what can I set this Q to be, right? How can I specify Q? Do you have any idea what is the best choice of Q that I could have? I want this distribution to give me samples which are around x, right? For the given x. What is the best distribution that is doing it? No, not Gaussian. It's going to be P of z given x itself, the posterior distribution. And if you don't see it, just pay attention. Everybody's looking? So I'm going to do a magic for you right now. This is the moment of disappearing the elephant. So now, say I set this Q to be P of z given x. Okay? Q is P of z given x. Remember, you have P of x given z. This is what is given to you. Now I am just changing, right? This is what we call it posterior distribution, right? So I am talking about the distribution of the latent for the given x, right? So I'm going to put Q to be P of z given x, right? Now, in the expression we had here, this was the expression that I was averaging, right? P of x given z, pz, here in the denominator I had q. I'm going to replace that q by P of z given x, right? So I'm going to put this guy P of z given x. Now, look at this guy. What is the denominator of this expression? Great. It's P of x given zi times P of zi, right? So it's going to be the joint distribution of x and zi, right? Now, if I write it down in this form, P of x and zi divided by P of zi given x, what is this guy? It's Bayes' rule. It's going to be Px, right? P of x and z is P of x times P of z given x, right? So this guy is essentially P of x. What can you say then? If I do importance sampling and I set Q to be exactly my posterior distribution P of z given x, what's going to happen? For every sample that I am computing that expression inside the expectation, for all of them, that expression is p of x, right? So essentially, if you set q to be exactly p of z given x, then with only one sample, you're going to estimate evidence with variance 0, absolutely 0, right? Because it doesn't matter what is z, right? Any sample is given, if you put it inside the importance sampling expression, it's going to be exactly p of x, right? So is one sample enough to do the estimation, right? Yeah, that is the challenge, right? Yeah, this is a good question. We're going to answer that one. But the key point here is that what we can claim now is that this good distribution Q, which we want to use in order to sample from and do important sampling, that Q should be something looking like posterior, right? If it is exactly posterior, actually the problem is solved, right? If it's not exactly like the posterior, we can try to make it close to the posterior, right? Everybody got the idea? So if you do the importance sampling with posterior, Bayes' rule tells you that essentially you are not doing any estimation anymore. I mean, with one sample, you're really computing the evidence that you want, right? So, moral of the story, a good distribution, good choice of this Q is the one which is close to the posterior distribution, right? Posterior distribution itself is the best ever distribution, right? But the problem is that, as you might guess, you cannot compute the posterior, right? So pay attention to this point. The posterior distribution, you cannot compute it, right? Because if you want to write it down in terms of things that you have, it's going to be p of z, x given z times pz. This is the joint distribution divided by px, right? And what is the denominator here? It's evidence itself, the thing that we are looking for, right? So finding the posterior is as complex as finding the evidence, right? So don't panic. We're not solving an NP-hard problem here. The point is that we're just reforming the problem. So in terms of complexity, it is still very complex to find the posterior. It's as complex as evidence. But the key point here is that we have some metric for explaining what is the right choice of Q, right? And this is very important because it's going to help us come up with one approximative solution. So everybody got the idea? So good Q is the one which is mimicking or getting very, very close to the posterior distribution P of z given x, right? So this is the best one. So in practice, since this is the same complexity, we cannot do it. The way that we do it is that we somehow try to approximate it. We try to learn it by some neural network. And the key point here is that we come up with one objective which explains how we can learn that. Any question? No question? Okay, so if you got no question, then let's start with the main trick here that the whole variational inference is about. So the main trick here is that we are trying to somehow estimate this guy without knowing it explicitly. So we don't have access to it, but we want to somehow estimate this one. Some of you might guess that we can do it to some extent. Because, for instance, when we talked about the general maximum likelihood training, we said we want to minimize the KL divergence between our model distribution and data distribution. But we ended up with this fact that we really don't need to know the data distribution itself if we want to minimize that KL divergence or estimate of it, right? So same thing we can do here, okay? So let's do it together. So let's say that I have now a class of distributions Q. Now, don't confuse yourself by class of distribution Q. What I mean, I simply mean a neural network, for instance, right? This neural network has a bunch of parameters. If I change the parameter, you're going to give me different distributions, right? How we can do it, we explain it later in the next section when we start with the variational autoencoders. Right now, I assume that I have lots of Qs, right? lots of candidates, and among them I want to find the guy which is the best guy that I can use when I want to do importance sampling, right? If I want to do that, what should I do? I should find the guy, the Q, which is looking very like the posterior, right? So what I can say, okay, I come up with the KL divergence. This is a metric which is explaining how much Q is different from the posterior. And then I try to find or select the Q distribution, which is looking like or closest to that posterior distribution, right? So here, what I'm doing, I am putting this notation, so given x, okay? I just do it to make the whole thing compact. But I guess you understand what I mean here, right? So this given x, I mean q of z given x, right? But I just keep this given, because if I drop it, then p itself is like both distribution of z and p of z given x, so I don't want to confuse you, okay? So that given, I simply indicate that this is conditioned to x value, right? So what I want to do, I want to find the q distribution, which is closest to the posterior distribution of z given x, right? But the key point, the key challenge here is that if I want to solve that optimization, I need to find the objective. The objective depends on the posterior distribution. I don't have the posterior distribution, right? Okay, no worries. Let's open it up, right? So let me write down the KL divergence between Q and the posterior, okay? How can I write it down? I can write down the definition. It's going to be the expectation over the first distribution Q, right? The expression inside the expectation is log of Q z given x divided by P z given x, right? This is the definition of KL, right? Cool. Next thing that I'm going to do, I'm going to multiply P of x with numerator and denominator, right? It's not going to change anything, right? And attention. I think I said it like 1,000 times. X is has nothing to do with z, right? X here is a fixed value, right? So that px over px, I can even take it out of expectation, right? Nothing going to happen. X is fixed for us, right? So P of x in numerator and denominator. Clear? Now, what is the denominator here? The joint distribution of z and x, right? I write it down P of x and z, and in denominator I have my q times P of x, right? Correct? So P of x is the evidence, is the thing that I'm looking for. I don't know it, right? QZ given x, do I have it? Yes. This is the neural network, right? This is the distribution that I have, and I want to see whether this is close to the posterior or not, right? What about P of x given x and z, the joint distribution? Do I have it? Do I have P of x and z? I have it. Do I have it? I have it. I have P of x given z, I have P of z, right? I multiply them, it's going to be P of x and z, right? So this is the KL divergence between Q and P. So this is exactly the expression we had in the previous slide. Now looking at the denominator, I just use the chain rule. I'm going to write it down P of x given z times P of z, right? I can compute this because I have P of x given z. This is the model which is taking z to x for me, right? And I have the prior distribution of the latent pz, right? So I have both of them. I can compute that one, right? Now I am over with my modification. I'm going to open up that logarithm term, okay? So the first thing that I'm going to do, I'm going to keep q in numerator and z in denominator. It's going to be my first logarithm term, okay? The next term that I have is 1 over p. Since it's logarithm, it's going to be simply a summation, right? So it's going to be plus logarithm of 1 over px given z, right? And the last term is going to be px. So it's going to be a logarithm of px. Okay? Everybody's cool? So I didn't do any magic, nothing specific. I just multiplied px in numerator and denominator, and then I opened up the final term, right? Now, let's look at this expectation for every single of these expressions to see how does it look like. So let me start with the first expression. This is the first expression. Q, once again, is the distribution that I am modeling. So this is the one neural network, whatever you want to think of. This is one distribution that I have, and I want to see whether that is close to the posterior or not. PZ is the prior of my latent, and I again have access to it. Now, one question. What is this expression here? This is the KL divergence, exactly. This is expectation over Q, log of Q over P, right? Expectation, first distribution, log of first distribution divided by second distribution, right? So this guy is a KL divergence between Q and the prior latent distribution, right? Now, can I estimate this guy? I mean, the slide says that we can estimate it, right? How can we estimate that one? I mean, if I want to estimate this expectation, I need samples from Q. I have Q, I can sample it, right? I also need to know what is the value of PZ at those particular samples. I have PZ, I can compute it, right? So I can estimate this. This is quite easy to estimate, right? So if I want to estimate this guy, I'm going to sample this QZ given X. This is the distribution that I have. This is my model, right? And then once I have these samples, I'm going to put it inside Q. I'm going to put it inside P. And then I'm going to estimate this whole expression by this average, right? I can do this estimation. This is something that I can estimate, right? So that is not a big deal. Clear? This is the first term. What about the second term? The second term was the expectation with respect to Q, the model distribution, log of P of X given Z, right? So log of 1 over P, I can write it down minus log. Yeah, that's fine, right? Now, looking at this expression, can I estimate it? Can I compute any estimation on that? Following what we did in the previous slide. Yes or no? What do I need if I want to estimate it? I need a bunch of samples from which distribution? Q. Can I sample it? Yes. Then I need to compute P of X given Z at those samples of Z. Can I do it? Yes, because I have P of X given Z, right? So I have Q, I can sample it. I have P of X given Z. Oh, I think there is a mistake. Okay, a very bad typo. Sorry. It's going to be X given Z. So this here. So this is a typo. Just fix it. Okay. I can compute P of X given Z, like the one which I have inside the summation. And then I can do the estimation, right? That is not a big deal. I can also compute an estimator of this guy, right? What about the last term? This was the last term, right? So the last term was log of px, okay? If I take expectation of log of px with respect to q, what's going to come out of this expectation? What do you think? Don't think complicated, it's super easy. Log px itself, right? Log px, does it depend on z? No, right? So it's going to come out of the expectation, right? Yeah, because that is not a function of z, right? So I can write down the definition of the expectation. Then I'm going to say, okay, this log px is essentially not depending on z, so it's going to come out of integral. And that integral, whatever q is going to be 1, because this is a distribution on z, right? And at the end of the day, it's going to be log px itself. This is the logarithm of the evidence itself, right? Clear? Everybody's cool? Now that we have done this, let's just put everything that we had. We had computed 3 terms. These 3 terms were the terms which were computing the KL divergence between Q and our posterior, right? So we wanted to compute this red term, which is quite complicated because we don't have the posterior distribution. Then we wrote it down in form of these 3 expressions. The first one was 1 KL divergence. The other one was this particular expression, so expectation of this logarithm. And the last one is log evidence, right? Those terms which are blue, can I estimate them? Yes, right? The red term is, though, something that I cannot estimate, right? So I have written this term in terms of something that I can estimate, plus the evidence, which I don't have access to, right? But the key point here is that the terms which are depending on Q are those which I can estimate, right? So if I want to do anything here, any optimization on Q, I don't really need to think about this guy. I only need to work with these 2, right? And these 2 I can compute, right? I can estimate. So this is a kind of tractable way that we can actually minimize that KL divergence without the need to know the posterior distribution itself, right? So let me put it in this form for you. So we wanted to minimize the KL divergence. The challenge was that we did not have this posterior distribution P of z given x. Well, if we replace that expression, we're going to minimize this expression. And here, when I am minimizing everything over Q, Q is showing up in the first expression, Q is showing up in the second expression, but this is not depending on Q, right? So I can forget about it, right? So minimizing this one is equivalent to minimizing this term, right? And this objective that we have, can you now estimate it? The answer is yes, right? I can estimate it, right? As we have seen in the previous slides. So we are more happy to, instead of writing down the minimization, we write it down in form of maximization. And here I am just, changing the sign, right? So it's going to be a log, the expectation of the log term minus the KL divergence, right? And this particular objective that we have, and we want to maximize, this is something that we can tractably estimate it using the samples we take from our model, right? Everybody's clear? Questions? I mean, I do understand that it is not a very simple thing. It has lots of computations, but I hope that you can track the main idea, right? So, I mean, to be honest, the first time I learned it, long time ago, it was also challenging for me. And to be honest, also, I have taught it several times in different ways. This was, to me, the easiest way. Yeah. But I do totally understand. I mean, you just need to repeat it over and over. At some point, it's going to get totally easy for you. Questions? No question? OK, cool. So if you got no question, moral of the story, if you want to minimize that KL divergence between the distribution Q and the posterior, you really don't need to know the posterior or evidence, because essentially, like maximum likelihood, essentially you really need some expression which is not depending on them. And as long as you can estimate that expression, you are fine. And given that this is a totally tractable expression to estimate, you are fine, actually. OK? Now, this expression that you have here, this is what we call it evidence lower bound, ELBO. Yeah? So evidence lower bound is essentially this expression that if I maximize it, it's going to be equivalent to minimize the KL divergence between Q and the posterior, right? This is what we call it evidence lower bound. And the key point about the evidence lower bound is that I can estimate it, right? So I can estimate both of these expressions. KL divergence, I can estimate it. This particular expression, again, I can estimate it by sampling. And ELBO, the evidence lower bound, this is something computable, whereas the evidence itself is not computable. Okay? Now, key property of ELBO is that if I think about a general, set of distributions Q, if I maximize this ELBO over those distributions, this is equivalent to minimize the KL divergence over those distributions, right? And this is a good thing because I have trouble with computing KL divergence between Q and the posterior, but I don't have problem with computing the evidence lower bound. Now, you might tell me why we call it evidence lower bound. This is not a very hard thing to show, right? So let me just write down that equality that we saw. So this was the equality. This was the bad KL divergence, which we cannot compute. This was the guys which we could compute. This is log of the evidence, right? Clear? Right. What is those good guys? What are those good guys together? ELBO, but minus ELBO, right? Yeah, so because ELBO, this is ELBO, right? Log minus KL. This is KL minus log, right? So this is minus ELBO, right? So I'm going to write it down minus ELBO. It's going to make the notation easier. And now if I play around with it, I keep log of PX, log of evidence on one side. I take ELBO to the other side, right? So it's going to be in this form. So log of evidence is the bad KL divergence plus ELBO, right? Everybody's cool? Now, that KL divergence, can it be negative? No, it doesn't matter what Q is, KL divergence is always positive or at least 0, right? So this means that this log of evidence is always larger or equal to the ELBO. This is why we call it evidence lower bound, because it's bounding the log of evidence from below, right? So this guy, this red term is always positive or 0. If it's 0, then ELBO is exactly log evidence. If it is non-zero, then log of evidence is going to be more, right? So ELBO is always something smaller than log evidence, right? But this ELBO, even though it's a lower bound, it has very good properties. The first property, as we said, is that this ELBO is going, the first property is that we can easily estimate it. This is fine. The other property, which is very important, is that if we think about the ideal maximization of this bound, okay, then we're going to exactly end up with the log of evidence. So let's look at it together. So log of evidence is the bad KL plus ELBO, right? Now, think about the case where I can actually realize any Q distribution, okay? So that Q distribution that you see here is any possible distribution ever, okay? If I really have that case, when I maximize this ELBO, what's going to happen? If I maximize ELBO, the bad KL, the red KL, is going to be minimized, right? And what is the minimum value of that? It's 0, right? If Q could be any distribution, then it's eventually going to be the posterior distribution, which is going to be exactly 0, right? Clear? So what I can say if ELBO is ideally maximized, optimized, then the KL divergence is 0 indeed for that optimal point. And this means that when I have optimal ELBO, that guy is exactly log of the evidence, right? Log likelihood. So it's not a simple lower bound which is smaller, right? When you maximize it, it's going to really touch the log of evidence. So this is a kind of tight lower bound, right? And this is a very good property. So I don't really need to worry about the fact that if I maximize ELBO, I'm not going to hit that, or I'm going to land somewhere totally different from the evidence, right? If I could really maximize it, then this is going to be exactly the log of evidence. So this is the key property. So log of evidence is going to be given exactly with the maximum of ELBO if we think ideally. And this means that ELBO is able to compute the log likelihood for us. It's not simply a lower bound. It's really computing it when it's maximized. So this is the second key property, that the maximum of ELBO is exactly the log evidence or log likelihood in our case. Everybody's cool? Questions? No question? Okay, so if you got no question, I do know this was a very long story, very boring story, but I can wrap it up here for you. So the key point in the variational inference is that we have this setting. We have a prior latent PZ. We have access to that. We have the conditional generator, P of x given z. What we are looking for, we are looking for a way to estimate the evidence Px, right? The evidence, which is essentially the likelihood for us. If you want to do it, variational inference tells us this. Go and compute ELBO. That one you can compute it. Once you computed that one, try to maximize it. When you maximize it, you're going to end up with one Q, which is very close to your posterior distribution, right? It's not exactly that guy, unless your neural network, which is explaining Q, is huge, right? But it's going to be somewhere close to that, right? Once you have that one, go ahead and use importance sampling with that Q, right? And then the estimator that you get is going to be your evidence, very close to your evidence, a very low variance estimator of your evidence. Yeah? So this is the idea of variational inference. And even though the whole story was quite long, it's quite easy to formulate it computationally. Is it OK? I do know you're super tired, but there are only 2-3 slides. Is it OK that I explain how you can use a neural network to do this? Yeah? OK. So now that we have the variational inference solution, then let's look at the case where we want to get a neural network and train it in a way that it's going to do what variational inference is suggesting. Okay? How can I do it? I can simply just think about one neural network, which is representing Q, right? We're going to talk about the specific neural network that does it later in the next section when we talk about variational autoencoders. But in general, what we can say, OK, let's say we have one Q, which is computationally is a neural network, right? I have a neural network with parameters W, which is explaining a class of distributions. The thing that I'm going to do, I'm going to initiate that neural network, and then I'm going to go inside the training loop. I sample from the bunch of latent samples from the exact distribution that I have, the Q, right? This is the class of distribution, my neural network, right? I'm going to sample from the neural network. So I'm going to have latent samples from that neural network. Then I go inside the loop. For every single sample, I'm going to compute the ELBO. I can compute this guy because I have this P of x given z. This is given to me. I have QW of z. This is, again, my neural network. I have P of z. This is my prior distribution, right? So I compute all of them at the particular sample. This is one sample of ELBO, right? If I do n different samples, then at the end of the day, I'm going to get an estimator of ELBO. For every sample, I'm going to backpropagate over the network, right? I'm going to have the gradient of the ELBO with respect to the weight, and then I use the average of those gradients to update my weight, right? And I keep on doing this till my neural network converges. That guy is going to land me somewhere close to the posterior distribution, right? If the neural network is a super duper deep one, it's exactly the posterior, almost, right? Now that I have this guy, then the whole story is over because I have Q. I can use it to do importance sampling, right? I'm going to get this Q. I'm going to take a bunch of samples from it, n different samples. For every single sample, I'm going to go compute the importance argument. And then that importance argument is one sample, right? Once I average those importance arguments, I'm going to get an estimator of my evidence, right? So whatever we have done here, you can do it by a neural network. Yeah? And if you want to really just think about computational thing, you only need the last 2 slides, right? But if you really want to do why you're doing it, you need all of the other slides. Everybody's clear? Yes?
Why do we call it variational inference?
Because you do know that the right inference is given by the posterior, right? But you don't have the posterior, so you're going to put a variational assumption on that, which is Q, and then you try to find the right one, right? This is what we call it variational inference, right? And by the way, one interesting fact. You know Michael Jordan, right? Now, the basketball player, the guy who is, this is the guy who like did a lot of things on this variational inference. So the variational inference framework was essentially in 90s developed by him, but then left for some time, and then again people get back to it when it started to be variational autoencoders. So variational inference is much older than all of generative AI. Like it's a kind of old framework. But people thought like it's a bunch of mathematical things, no application, till it ended up with variational inference autoencoders. So that's pretty much this. So I'm happy that I could finish this section. So what we're going to do next time we're going to have a better lecture, because we are going to think about real neural network. We want to see how we can really use this variational inference to somehow train the probabilistic generator that we talked about at the beginning of this lecture, right? And you can guess that this one is not quite complicated. Because if you remember, we came up with this idea that I have this probabilistic generator, right? This was the Gaussian distribution with parameters specified by the neural network, right? This was the generator we had. And what we wanted to do maximum likelihood training, meaning that we wanted to maximize the log of the likelihood, right? And we ended up with this challenge that if I write down that term, is going to be this integral, and this is not feasible to compute, right? But right now, I do know how to compute that one, or at least estimate it, right? What I can say log of the evidence, or log of the likelihood, is essentially the maximum of the ELBO, right? So I can do that. I can compute this if I have enough computation. And then since I want to maximize the likelihood, I need to maximize that ELBO, not only in terms of W, but also in terms of the